In question 7 of the series, we're asked to integrate the function dx over the square root of x squared plus 9. To do this, we'll need to match the bottom expression with one of these expressions. And you'll notice that the square root of x squared plus 9 matches this one, where our constant 9 matches the a. And given that this a is being squared, that means our a value would be 3. With that being said, what I will do is set x equal to a times tangent theta, where, as mentioned before, a is equal to 3. 3 times tangent theta. Let's visualize what this looks like on a right triangle. On a right triangle, we would have theta, and remember, tangent relates opposite over adjacent. So our opposite would be x, and our adjacent would be 3. And our hypotenuse would have to be x squared plus 9. You can prove that using the Pythagorean's theorem. Going back to here, I'll take the derivative with respect to theta, and that gives me dx over d theta 3, and the derivative of tangent theta, you probably know this, it's secant squared theta. Next, I'll solve for dx so that I can replace this dx with an expression that's in terms of theta, giving us dx is equal to, multiplying both sides by d theta, 3 secant squared theta d theta. So, in my next step, I'll substitute what this is with what we found, and I'll substitute this x with what I set it as, giving us the integral of 3 secant squared theta d theta over, and at the bottom I'll write down the square root of bracket 3 times tangent theta squared plus 9. Multiplying this 2 into these two components gives us the following. The integral of, once again, 3 secant squared theta d theta over 9 tangent squared theta plus 9. Factoring out a 9 from the denominator gives us 9 bracket tangent squared theta plus 1. Square rooting that over our numerator, which hasn't changed. Notice that we have two factors within the radicand underneath the radical. So I can distribute this radical to the 9 and to this other factor, which gives me the integral of, once again, 3 secant squared theta, and the square root of 9 is 3. So I'll pull that out. That will cancel out with this 3. And still underneath the radical is tangent squared theta plus 1. Now, if you recall, in the original table, there was an identity that goes along with using this substitution, and that identity was 1 plus tangent squared theta is equal to secant squared theta. So what we had underneath the radical can be switched with secant squared theta. And if we switch this with secant squared theta, square rooting a square gets rid of the square root. So we're left with, in the denominator, simply secant theta, and at the top, secant squared theta d theta. We have two secants up here, one down here. This will cancel out with the one up there. And now we have to integrate secant theta with respect to theta. Now the integral of secant theta, this is a known integral and we won't prove it in this video, is equal to ln absolute of secant theta plus tangent theta. So we have ln absolute of secant theta plus tangent theta plus c. Now originally our question was in terms of x, but this is in terms of theta. So what we have to do is go back to that triangle that we made earlier and find out what secant is. Secant is the reciprocal function of cosine, and cosine is defined as adjacent over hypotenuse. Therefore, secant will be hypotenuse over adjacent. Our hypotenuse is x squared plus 9, and that's square rooted. and our adjacent is 3. So I'll place that where I saw secant theta, and I'll also place x over 3 as my tangent theta. So let's go ahead and do that. We have ln of the square root of x squared plus 9 over 3 plus x over 3 plus c. Given now that both of these have the same denominator, I can combine this and use the log rules to simplify this further. X squared plus 9 square rooted plus x over 3 plus c. And now I can separate this as ln of the numerator minus ln of the denominator 3. This is a number. I can find that out using my calculator, but this should represent your final expression for question number 7. And there you have it. That is how to integrate using inverse trigonometric substitution. We still have 2 more questions left, so make sure to watch question 8 for another example.